So I will use the circuits that I used in my first video, that is the Thevenins Theorem, to solve this using Norton's Theorem. So you'll see that we should get the same answers when we are done. Okay, so this question says we should use Norton's Theorem to find the current in the 10 ohm resistor. So this is where the 10 ohm resistor is, and we know that in Norton the first step is to remove the resistor through which we want to find the current, the same as in Thevenin. And this time around we will short that side. Remember that in Thevenin we will find the open circuit voltage, but in Norton's we will short this side. So let's see how it will go. This will be the final circuit after you've short the place. So it will look like this, and then you will find your short circuit current, that is IN. We have 12 volts here, 6 ohm, 4 ohm, and your 10 volts here. So from here we know that this 10 volts will produce a certain current, let's say I1. This voltage source, this 12 volts, will also produce a current I2 here. And when I1 meets I2 on this junction, they will flow through this branch and it should give us IN. So from KCL we can say that I1 plus I2 should give us the value of what? IN. And from KVL we can write a loop equations here involving I1 and I2 to find the value of IN. So let's see what will happen. If I take this bigger loop, using KVL we equate the voltage source or the voltages, then we equate them to the voltage drops. So when we take this bigger loop going in the clockwise direction, I can say that 10 should be equal to 4I1. So from here I can find the value of I1, which is 10 on 4 amperes. And I can also take this loop and write an equation involving these voltage sources and the voltage drops. So I can say that 10 minus 12 should be equal to 4I1 minus 6I2. Why minus? Because we are going in the clockwise direction, but this current I2 is opposing our direction. So I can say that, simplifying this, I can have 4I1 minus 6I2. But I know the value of I1 already. That is 10 on 4. So I'll say that, let me group like terms. Okay. So I'll just fix the value of I1, which is 10 on 4 here. 6 minus 6I2, and this should give me minus 12 here and minus 6I2. And from here we can find the value of I2 when we divide through by minus 6. So I2 will be equal to 2 amperes. And from here I said that, from KCL I said that I1 meeting I2 should give us the value of what? IN. So real quick we can say that IN will be equal to the value of I1, which is 10 on 4, plus I2, which is 2 amperes, and we should have 9 on 2, which is the same as 4.5 amperes. So remember how we used to find the total resistance in Thevenin? The same thing will happen here. We will short or deactivate all sources in the circuit, and when they are voltage sources we short them. So in this case we have voltage sources. So this is how the circuit will look like. These are the terminals. So this is, in this case we will find Rn, just to indicate the name of Norton, right? There's nothing special about the N. So looking through this terminal, let's say AB, we can see that our Rn, 4 is in parallel with 6. So it will be 6 parallel 4. And this should give us 12 on 5 ohms. And we know that the equivalent circuit for Norton looks like this. You have your IN in parallel with your RN. Then you bring back the resistor that you took out, that is 10 ohm. And I have RN to be equal to 12 on 5 ohms and IN to be 4.5 amperes. So from current division, if you want to find the current flowing through this 10 ohm, so let's say I10 representing the current through the 10 ohm, it will be the opposite resistor out of the summation of these two times the total current. So it will be 12 on 5 all over 12 on 5 plus 10 times your total current, that is the IN, which is 27 out of 31 amperes. So I10 in decimal will be 0.871 amperes. So comparing this answer to the one I solved in Thevenin, if you looked at the first video I did on Thevenin, you see that it's the same current that we got here. So yes. Okay, so we'll use Norton's theorem to find the current in the 0.1 ohm resistor. So if you watched my video on Thevenin, you see that I solved this question using Thevenin. So let's see if we use Norton's theorem or apply Norton's theorem here, we'll get the same answer. Right, so this is what we do in Norton. As I said earlier, we take the resistor in question out and we short that side and we find the current there. That is the short circuit current, IN. So let's see, your new circuit will look like this. And we will short that side and the rest will be intact. So here is 2 amperes, 0.4 ohm, 0.5 ohm, here is 5 amperes, and we find the short circuit current, that is IN here. But real quick, let's take a look at this. You see that 5 amperes is flowing from this branch. It will reach here, so I can say that 5 minus IN will flow through this branch. That's a 0.5 ohm resistor. And let's look at this side. When this 2 amperes flows and reaches this junction, it will meet IN. So I will say that IN plus 2 will flow through the 0.4 ohm resistor. So from here, I can write a loop equation using this, and I should be able to find my IN. Very simple. So let's see. Using KVL, we say that we group the voltage sources on one side and we equate them to the voltage drops. So in this loop, since there is no voltage source, my voltage will be 0, and it should be equal to, I'm going through this direction clockwise, so I will say that 0.4 times the current, that is IN plus 2. This current is countering our direction, so I will say that this one will be minus 0.5 multiplying 5 minus IN. So with this equation, it will help us find the value of IN. So 0.4 IN plus 0.4 times 2, that is 0.8, minus 2.5, that is 0.5 times 5, plus, because we have negative, it will give us IN 0.5. So grouping like terms, I can add the INs. So I have to say that 0.5 IN plus 0.5 IN here plus 0.8 minus 2.5. 0 will be equal to 0.9 IN. And here will give us, negative 1.7. Yeah, negative 1.7. So I'll bring this to this side, so it will be positive. It should be equal to 0.9 IN, dividing both sides by 0.9 I should have the IN value, which is 17 on 9 amperes. This is very simple. I mean, this is very simple. And after finding your IN, Norton's theorem, the next step is to find your Rn. And in finding Rn, we deactivate all sources. And I'll say again, if they are voltage sources, you short the sources, and if they are current sources, you open. So in this case, you have two current sources. So we are going to open here and open here and look through the terminal here and find our Rn. So let's see. This will be the final circuit if you want to find our Rn. So we'll open this side and we'll open this side. Here is 0.4 ohm, here is 0.5 ohm. Looking through this terminal, you should find your Rn. You see that I've opened here because there was 5 amperes here. There was 5 ampere here, which is a current source. So I opened here. There's also a 2 ampere source here. So I open here, right? And I'll look through the terminals over here and find my Rn. So you can see that 0.5 will be in series with this 0.4, because if, for example, there's a voltage source here producing a current, the current won't flow in this direction because here is open. The current would also flow through this direction because here too is open. So it will flow through the 0.5 ohm through this branch and come back to wherever it started. So you can see that the same current is flowing through 0.5 and 0.4 ohm. So our Rn, which is the same as RTH in Thevenin, will be 0.5 ohm plus 0.4 ohm. So Rn should give us 0.9 ohm. Right, so then we'll come back straight to the equivalent circuits for Norton. We have your IN here, your Rn, and the resistor that you took out, that is 0.1 ohm. Here will be our Rn, that is 0.9 ohm, and this will be your IN. We found IN to be 17 out of 9 amperes. So using current division, we can find the current flowing through this one. So let's say I 0.1, that is the current flowing through 0.1, should be 0.9 out of 0.9 plus 0.1 times the total current, that is the IN, that is 17 out of 9, and this should give us 17 out of 10 amperes. So in decimals, this should give us 1.7. So if you watched my first video, you see that when we used Thevenin, we had current of 1.7 amperes, and using Norton's too, we had 1.7 amperes. Okay, so we are to find the current in this 5 ohm resistor using Norton's theorem again. So this is what we do. We take out the resistor in question and we find the short circuit current over there. So this is how it will look like after you've taken it out. And it is very important to know what to do at every point in time to get your final answer, or else you are wrong. Here is a 2 ohm, another 2 ohm, this is another 2 ohm, 3 ohm here, 2 ohm, 7 volts, and here is 10 volts, 10. So you see that this was where the resistor was. I took it out and I'll find my short circuit current, say IN. So from here, what you should do is that you should apply your KCL very well so that you can get the value of IN. So this is what happens. So let's say this 7 volts produces a current, say I plus IN. If I plus IN reaches this junction or this node, IN goes here. So that means I will flow through this 3 ohm. We have 10 volts also here. So let's say this 10 volts produces a current, say I3. I3 upon reaching this node will meet IN here. So IN plus I3 will flow through this 2 ohm resistor. And when this current, I mean the IN plus I3 gets here, I3 will go back to where it came from. So IN will flow through this 2 ohm resistor. So IN will meet I here, and they will come back to where they started. So that this means that my current division is right, and I can use this to find my IN. So taking this loop into consideration, I can write from KVL, I can write that 7 should be equal to 2 multiplying I plus IN plus 3I, because they are all in the same direction. That is why everything is positive. So if I simplify this, I should have 7 5I plus 2IN over here. So let's say this is equation 1. I can also pick this bigger loop and write an equation. So I will group the voltage sources, that is 10 and 7, and I'll equate them to the voltage drop, that is 1, 2, and 3. So it will be 10 plus 7 should be equal to 2 multiplying I plus IN minus 2I3 plus 2IN. Why is this negative? Because looking at this direction, we are going clockwise and this is countering our direction. So this will be minus 2I3 when we add this voltage drop over here. So simplifying this, should have 17 equals 2I plus 4IN minus 2I3. So let's say this is equation 2. And if I decide to pick this loop and write an equation, this middle loop, the voltage source in this loop is 0. So going clockwise direction, I can say that 2 will multiply IN plus I3 plus this 2IN, this is this, and this will be minus 3I because we are going clockwise and this is countering our direction. So I can also say that after simplifying this, we have minus 3I plus 2I3 plus 4IN over here. That is equation 3. So from here we apply the tools that we know using substitution and all that. So from here I can write equation 2 in this form. 17 should be equal to 2I minus 2I3 plus 4IN. So if I add equation 3 and equation 4 right now, equation 3 and equation 4 right now, I should get 17 plus 0, which is equal to 2 minus 3I, because we have 2 here and we have 3 over here. So it will be 2 minus 3 plus 2 minus 2 I3 plus we have 4IN here, 4IN, which will be what? 8IN. So I can simplify this. Here will be 17. This I3 will go out because minus 2 is 0. So it will cancel this I3 out. So I'll have minus I plus 8IN. So let me say this is equation 5. So looking at equation 5 and equation 1, we have equation 1 in terms of I and IN, and you have equation 5 in terms of I and IN. So we can use just our tools that we know, elimination and all that, to find the value of IN. And we will have IN to be equal to 46 on 2, 21 amperes, and our I to be 11 or 21 amperes. But what we are interested in here is just the IN. So after finding your IN, the next step is to find RN. And in RN, we deactivate all sources, and in this case they are voltage sources, so we will short them and we will find our total resistance. So let's say this is how the circuit will look like if I short this voltage source, and this will be my resistor. This resistor will be here. I'll have this resistance here, have this one, I'll have this one, and I'll short this voltage source. So here is 2 ohms, 2 ohms, 2 ohms, 2 ohms, 3 ohms, and this is my terminal in which I'll look through, let's say Rn. So from here I can see that 2 and 3 are in parallel. 2 and 3 are in parallel. This 2 and 2 are also in parallel. So 2 and 2 are in parallel, and they are all in series with this 2. So this will give us 6 on 5. This will give us 1 plus 2. So our Rn should be equal to 21 on 5 ohms. So since we've gotten our In, and our Rn, we can use the equivalent circuits for Norton to determine the current through the 5 ohm resistor. So here will be our 5 ohm, here will be our Rn, that is 21 on 5 ohm, and our In, which is 46 on 21 amperes. So 46 on 21 amperes. So using current division, we can find the current through this one, say I5. From current division, it will tell us to make this the numerator, so it will be 21 on 5 over the summation of both, that is 21 on 5 plus 5, all multiplying the total current, and in this case In, that is 46, 21. So I5, that's the current through this 5 ohm, should give us 1 ampere. So comparing this into my previous video in Thevenin, you see that we had the same answers. So we have to find the current in the QM branch. This is a QM branch using Norton's Theorem. So in other words, they are asking us to find the current that will flow through this resistor. Okay, so in Norton, this is what we do. We remove the resistor in question and we find the Norton's current, the short circuit current here. So the circuit will look like this. After removing it, will look like this. Here is our 6, and this will be our short circuit current, say In. Here is a 4.5, here is a 3 ohm, 4.5 ohm, 3, and here will be our source, 24 volts. So how do we find In? Before we can find In, we should know the currents flowing from this side and the one which will flow through this side and gets here, and the current that will flow through this resistor, and they will join here and flow through In. But before that, we don't know the currents flowing in this branch and in this branch. So what we can do is that we can find the total resistance and divide them by the voltage and get the total current coming from here, and we will use current division to get the currents flowing through this branch and this branch, and we can know In. So from this question, or with this question, we will find our RTH first, Rn, because this is Norton. So we'll find our Rn first. Alright, so this is how it will look like. This will be the 6. And in finding Rn, we short this voltage source. So it will look like this. So we find Rn. Here is 4.5 ohm. Here is 3 ohm. And here is 4.5 ohm. Here is 3 ohm. Here is 6 ohm. Okay, so looking into this terminal, we can see that if a current, or let's say there's a voltage source here, and it's producing a current. And when it gets to this node, the current that will flow through this 3 is the same current that will flow through this 4.5. So we can see that this and this are in series, and there will be a different current flowing through this resistor. So we can say that this is in series, and this and this are in parallel. And if a current is also flowing from this side, you can see that the current that will flow through this 3 ohm will be the same current that will flow through this 6 ohm. So we can see that 6 and 3 are in series, and they will be in parallel with this 3. So I can redraw this and make it very simple for you guys to see. So it will look like this. And this will be the terminals. These terminals, they are here. So I'm saying that 3 and 4.5 are in series. So from that I'll have 7.5 ohm, sorry, and they will be in parallel with this 4.5. So here is it. And from here I said that if a current is moving from this side, when it gets to this node, the current that will flow through this 3 will be the same current that will flow through this 6. So 6 plus 3 will be in series, which is 9 ohm, and they will be in parallel with this 3 ohm. So here's a 3. So our Rn will be very simple. This and this will be in parallel, and this also and this will be in parallel, and they will all be in series. So it will be 7.5 parallel 4.5 plus 9 parallel 3. So the Rn will be 8.1 out of 16 ohm, which is 5.0625 ohm. So now from here we can find the current, or the total current flowing from this source. So IT will be equal to the voltage over the total resistance. We have our voltage to be 24 and the total resistance to be 81 out of 16. So our total current will be 128 out of 27 amperes. So now we know that this current is, the current coming to this junction is 128 out of 27 amperes. So from here we can use current division to know the current flowing through this branch, and we know that after current goes to every resistor, it will join here and come back. So we know that the total current here also is the same 128 over 27. So from here we can use current division to know the current through this 4.5 ohm resistor. So let's see how it will happen. So we see that the total current coming to this junction is 128 over 27. So from here we can use current division to find the current through this one. So current flowing through the 7.5 ohm, because 3 plus 4.5 should give us 7.5 ohm. So the current through the 7.5 ohm will be the opposite resistor over the summation of both times the total current that we found already. So it will be 3 out of 3 plus 7.5 times the total current, that is 128 out of 189. Sorry, here is 27, right? Let me write it again. Times 128 out of 27, and this should give us 256 out of 189 amperes. So the same way we know that after this current going through every resistor and coming back, it should join here and come back to the source. So we know that the total current here is also 128 out of 27. So from here we can use current division to find the current through this IN. So the current here coming from this side and the current from this side should give us the current IN. So now the current in the 4.5 ohm resistor will be the opposite resistor out of the sum of the resistors times the total current. So it will be 9, because we have 6 and 3, so it will be 6 plus 3, which is 9 out of because we have 6 and 3, so it will be 6 plus 3, which is 9, out of 9 plus 4.5 times the total current, that is 128 out of 27, which will give us 254 out of 81 amperes. So the difference between this and this should give us the IN, because this is coming this way and this will go this way, but we want the current in the opposite direction, this, so that this will meet this and will flow through this direction. So I can say that IN will be equal to the current in the 7.5 ohm minus the current in the 4.5 ohm because of the direction. So I can say that we know the current for this, that is 256 out of 189 minus 254 out of 81, and this should give us minus 1010 out of 567 amperes. So we know our IN, that's the short circuit current, so, and we know our RN. So what is left is to use the Norton's equivalent circuit to find the current through the 5 ohm. So here will be 5, here will be our RN, that is 5.0625, and our IN is minus 1010 out of 567. So using current division, we can find the current through this 5 ohm. So current through the 5 ohm will be equal to 5.0625 out of 5 plus 5.0625 times minus 1010 out of 567, which should give us negative 0.900 amperes. So the negative here is just showing the direction, which means that this IN should have faced this way rather, not this way. So it is just showing direction.